In late August 2025, a team of researchers working with the James Webb Space Telescope pointed its NIR spec instrument at a small, fast-moving visitor passing through our solar system and found something that, according to their own published paper, didn't match a single known comet in recorded history. Not one. Every comet ever studied in detail, whether it came from the icy edge of our own solar system or somewhere closer in, releases a predictable mix of gases as it warms near the sun. Mostly water vapor, with smaller amounts of carbon dioxide and other trace gases mixed in ratios astronomers have documented carefully across decades of observation. This object was doing almost the opposite. It was drowning in carbon dioxide and barely venting any water at all. And within days, a second team, working independently on a completely different telescope, found something even stranger sitting inside the same cloud of gas. A metal that, according to one of the astronomers involved, comes from a chemical process nobody has ever directly observed before in any comet, anywhere. The object is Comet 3IATLAS, and what Webb has revealed about its chemistry over the past year is the kind of discovery that doesn't need any exaggeration to sound incredible, because the actual published numbers already do that on their own. This isn't one finding, it's a whole sequence of them, gathered carefully across nearly a year of continuous observations, each one adding a new layer to a chemical portrait that, as of this year, has become the most detailed record of material from another star system that humanity has ever assembled. Built not by traveling to another star, but simply by pointing the right instrument at the right object at the right moment, and then doing the painstaking analytical work to make sense of what came back. Let's set the stage quickly. For anyone catching this story mid-flight, 3IATLAS was discovered on July 1st, 2025, by the NASA-funded ATLAS Survey Telescope in Chile, and its orbit immediately marked it as something rare and genuinely significant. Only the third confirmed interstellar object in recorded history, following Oumuamua in 2017 and Borisov in 2019, meaning it originated from outside our solar system entirely and was only ever going to pass through once, on a trajectory too fast and too open a curve to ever have been captured by our sun's gravity. What made 3IATLAS different from the two interstellar visitors before it is that it arrived active and bright enough, early enough, for nearly every major space telescope humanity currently operates to get a real, detailed look at it before it faded from view. And it's that detailed look, specifically from Webb, that produced the two findings this story is actually about. Findings that, taken together, ended up telling scientists something about the deep history of this object that neither discovery could have revealed entirely on its own. The first came from Webb's NIR spec instrument in observations taken while the comet was still 32 astronomical units from the Sun, well before its closest approach, at a distance where most comets are still relatively quiet, not yet active enough to produce much of a coma at all. According to the paper describing those results, led by NASA Goddard astronomer Martin Cordner and 12 co-authors, the spectral images revealed a coma, the cloud of gas and dust surrounding a comet's solid nucleus, that was dominated overwhelmingly by carbon dioxide. Specifically, the ratio of carbon dioxide to water in that coma came out to 7:6, with an uncertainty of just 0. 3. To put that number in context, most comets native to our own solar system show a carbon dioxide to water ratio well below 1 at a comparable distance from the Sun, meaning water typically outweighs carbon dioxide in the gas being released, sometimes dramatically so, since water ice is generally the dominant component locked inside a typical comet's nucleus. 3IATLAS was doing the reverse, and by a wide margin. The paper describes this measurement as among the highest carbon dioxide to water ratios ever observed in any comet, and states plainly that it sits 5 standard deviations above the established trend line that astronomers use to predict how comet composition should behave at a given distance from the Sun. In scientific terms, a deviation that large isn't a minor curiosity, the kind of statistical wobble you'd expect from ordinary measurement noise or a small, unrepresentative sample. It's close to definitive evidence that something about this object's chemistry or its history genuinely doesn't follow the pattern every other well-studied comet follows. It's worth explaining why that matters so much, because on its own, more carbon dioxide than water might not sound especially dramatic if you don't know how comets normally behave. As a comet approaches the Sun, its surface heats up, and different ices trapped in that surface begin to sublimate, turning directly from solid ice into gas without ever passing through a liquid stage, at different temperatures. Water ice requires relatively more heat to sublimate, so it typically only becomes highly active once a comet gets fairly close to the Sun, usually somewhere inside the orbit of Mars. Carbon dioxide ice, on the other hand, sublimates at much colder temperatures, meaning it tends to dominate a comet's activity earlier, while the comet is still relatively far out, before enough heat has built up to really get the water ice going. Astronomers have studied this pattern across dozens of well-observed comets over the past several decades, building up a reliable trend line that predicts roughly how much carbon dioxide, relative to water, a typical comet should be releasing at any given distance from the Sun. What astronomers observed with 3IATLAS wasn't simply, it's still far from the Sun, so of course carbon dioxide dominates for now. The measured ratio was so extreme and sat so far outside the normal range, even accounting for distance, sitting at that reported 5 standard deviations above the trend line, that the Webb team concluded it likely reflects something intrinsic to the nucleus itself, meaning the comet isn't just early in its warming cycle, it may genuinely be built from unusually carbon dioxide-rich material all the way through, in a way that's fundamentally different from the water ice-dominated comets native to our own solar system. For comparison, the paper notes that the only other comet ever observed with a ratio in a similar range was an unusual object called C 2016 R2, itself widely regarded among astronomers as one of the strangest comets ever studied, known for its own bizarre chemistry and an unusually blue-tinted ion tail, meaning 3IATLAS isn't just an outlier compared to ordinary comets. It's an outlier even compared to the handful of other objects that were already considered chemically unusual before it came along. So, where does that kind of composition come from? This is where the story gets genuinely fascinating, because the leading explanation scientists have proposed isn't about where 3IATLAS formed. It's about what happened to it afterward, across an almost incomprehensible span of time. Stephanie Milam, an astrochemist at NASA's Goddard Space Flight Center who worked on the Webb observations, offered an explanation reported by Smithsonian Magazine. Floating through the near-absolute zero void of interstellar space for eons, constantly bombarded by cosmic rays, high-energy particles that stream through the galaxy at close to the speed of light, originating from sources like supernova explosions scattered across the Milky Way. 3IATLAS may have developed what she described as a cooked shell on its surface, a layer where those cosmic rays gradually broke down and rearranged the comet's original ices over billions of years, effectively baking a carbon dioxide-rich crust into existence on the outside of the nucleus, distinct from whatever ices might still be locked away deeper inside, unaltered and preserved in something closer to their original composition. That excess carbon dioxide, according to Milam, is now simply being heated by our Sun for the first time in this comet's entire existence and venting outward into the coma that Webb photographed. It's a genuinely elegant idea, because it doesn't require 3IATLAS to have formed in some exotic, carbon dioxide-saturated corner of another star system at all. It only requires enough time and enough radiation exposure, both of which this object appears to have in staggering abundance, far beyond anything a comet native to our own solar system would ever accumulate across its entire lifetime orbiting the Sun. If that explanation holds up, it means the specific chemistry Webb measured isn't really telling us what kind of star system 3IATLAS originally formed in. It's telling us something about the sheer duration of the journey it took to get here. A surface chemically weathered not by wind or water, the way rock erodes on Earth, but by a slow, relentless bombardment of cosmic radiation sustained across a stretch of time longer than our own solar system has existed. And that connects directly to a separate, much more recent finding, because the carbon dioxide story turned out to be only half of what Webb eventually revealed about this comet's age. In a paper published in the journal Nature on June 22, 2026, the same Cordner-led team returned to Webb's NIR spec data, this time analyzing something even more subtle than the overall gas composition, the specific isotopic ratios locked inside individual molecules in the coma, a level of chemical detail that requires extremely precise spectroscopy to even detect at all, let alone measure with the kind of confidence needed to build a scientific case around it. According to NASA's own summary of the findings, the spectrograph detected only traces of carbon-13 compared to the much more common carbon-12, a signature that points toward an extremely old origin, since galaxies steadily accumulate carbon-13 over billions of years, as successive generations of stars are born, live, and die, gradually enriching the surrounding gas with heavier elements through processes like nova explosions. Combined with unusual deuterium ratios in the comet's water, deuterium being a heavier form of hydrogen that builds up specifically in extremely cold, ancient interstellar environments, colder than almost anywhere our own solar system's icy bodies ever formed, even out past the orbit of Neptune. The team concluded that 3IATLAS could be as old as 10 to 12 billion years, making it, if the estimate holds, one of the oldest physical objects any human being has ever directly measured up close, potentially formed before our own Sun ever finished forming at all. That age estimate and the cosmic ray weathering explanation Milan proposed for the CO2-rich coma fit together into the same larger picture, an object that has spent an almost unimaginable length of time drifting alone through the galaxy, being slowly reshaped by radiation exposure, Most solar system comets never experience even once across their entire history, simply because they've never spent anywhere near that long adrift in interstellar space to begin with. In other words, the two headline discoveries this story is built around, the extreme carbon dioxide ratio and the age revealed by isotopic chemistry, aren't really two separate stories at all. There are two different instruments independently pointing toward the same underlying explanation, one confirming what the other implied. Now for the second discovery, and this one arrived at almost exactly the same time as the carbon dioxide result, from a completely different instrument entirely. While Webb's NIR spec team was analyzing gas composition, a separate group using the Very Large Telescope in Chile, a ground-based observatory array run by the European Southern Observatory, distinct from Webb but capable of its own detailed spectroscopy, was studying the same comet's coma and found something that, according to Thomas Puzia, an astronomer at the Pontifical Catholic University of Chile who worked on the analysis, genuinely surprised the team. They detected clear, unmistakable nickel. On its own, that's not unusual. Nickel has been detected in other comets before, including in 2I Borisov, the previous confirmed interstellar visitor, and in a number of comets native to our own solar system as they pass close enough to the Sun for trace metals locked in their nucleus to sublimate directly into gas form, a phenomenon astronomers only fully recognized as common within the past several years, after decades of comet spectroscopy had somehow missed just how widespread it actually was. What made this detection strange was what was missing alongside it. In every previously studied comet where nickel has been detected sublimating into the coma, it has always appeared together with iron in roughly consistent proportions, because the two metals are typically locked together in the same underlying compounds within a comet's nucleus and released together as that material heats up. The two elements behave almost like chemical siblings in this context, rarely, if ever, showing up meaningfully separated from one another in any previously studied object. 3IATLAS broke that pattern completely. The VLT team detected substantial nickel in the coma, and essentially no corresponding iron at all. According to Puzia's own account of the finding, that combination is a genuine conundrum, one that suggests the metal is being released through some previously unrecognized chemical process, something never directly observed in a comet before. The leading explanation the VLT team proposed involves a specific, genuinely exotic molecule called nickel tetracarbonyl, a compound where a single nickel atom is bonded to 4 separate carbon monoxide molecules, forming a highly volatile structure that notably requires no iron to exist at all. This isn't some entirely theoretical substance dreamed up to explain an anomaly. Nickel tetracarbonyl is a real, well-characterized chemical compound, studied extensively here on Earth precisely because of how easily it forms and how readily it breaks apart under mild conditions, properties that made it useful industrially long before anyone thought to look for it in a comet, in processes ranging from metal purification to early experiments in vapor phase chemistry. According to the researchers' own reasoning, if 3IATLAS's nucleus contains dust grains built from nickel tetracarbonyl, rather than the more conventional nickel-iron compounds found in solar system comets, then exposure to ultraviolet light from the sun could break the molecule apart efficiently, releasing free nickel atoms into the coma alongside carbon monoxide gas, all without needing to liberate any iron in the process, since the iron simply was never part of the compound to begin with, having been excluded from the molecular structure entirely from the start. If that's what's actually happening, it would help explain something else astronomers had already noticed about 3IATLAS. It was unusually active for an object still relatively far from the sun, producing more gas and dust earlier in its approach than a typical comet of comparable size, moving at a comparable distance, would ordinarily be expected to. A volatile compound like nickel tetracarbonyl, which breaks down easily under UV exposure even at low temperatures, could plausibly help drive that early elevated activity, adding one more piece to the picture of an object whose surface chemistry behaves nothing like the comets astronomers have spent over a century cataloging within our own solar system, using instruments that, until Webb, simply weren't sensitive enough to catch a signature this subtle in an object this faint and this far away. It's worth being clear about where the science currently stands on this, because both major findings, the carbon dioxide dominance and the iron-free nickel, were still being actively studied and refined even as later observations came in. When Webb returned to 3IATLAS after its closest approach to the Sun using a different instrument called MIRI, the mid-infrared instrument, for 2 observing sessions in mid to late December 2025, the picture shifted again in an interesting way. According to that follow-up paper, the post-perihelion carbon dioxide to water ratio had dropped to roughly half of what it measured before perihelion, and the team detected something new entirely. A robust signal of methane gas, a hypervolatile ice that sublimates at even lower temperatures than carbon dioxide, meaning it should, in principle, be among the very first things to boil off a comet's surface as it warms, not something that shows up only after the comet has already rounded the sun and begun heading back outward. The fact that methane production actually increased between the 2 December observing sessions, rather than tapering off the way you'd expect from a simple surface layer being progressively used up, raised its own set of fresh questions about how deeply layered and how chemically uneven this nucleus really is beneath its outer crust. One possibility researchers have floated is that the comet's rotation is periodically exposing fresh pockets of methane-rich material that had previously been shielded from sunlight, essentially uncovering new deposits as different faces of the nucleus rotate into direct solar exposure, the way turning a frozen roast on a spit exposes new surface to the heat with every rotation, though that remains an open hypothesis rather than a settled conclusion. The same December data also confirmed something the earlier nickel detection had only hinted at. Atomic nickel showed up clearly in Webb's own spectrum too, at a wavelength of 507 micrometers, matching what the VLT team had found from the ground months earlier, giving the metal detection independent confirmation from a second, completely different observatory using a completely different technique, entirely removing any concern that the original ground-based result might have been some kind of instrumental artifact or measurement error. Taken together, what these observations paint is a picture of a comet with a genuinely layered, complicated history written directly into its chemistry. A carbon dioxide-rich outer crust, likely baked into existence over billions of years of cosmic ray exposure during an unimaginably long journey through interstellar space, sitting above deeper layers that appear to still be releasing hypervolatile methane well after the comet's closest pass by the sun, all of it laced with a nickel signature that doesn't behave like nickel is supposed to behave in any comet ever studied before, based on a chemical pathway that had never been directly confirmed in space until this specific object came along to demonstrate it. Thomas Puzia summarized what this means for the field in a way that's hard to improve on. This work, he said, essentially cracked open the door to a whole new world of chemistry that scientists never had direct access to before, not because the chemistry itself is unknown to physics or laboratory science, since compounds like nickel tetracarbonyl have been studied on Earth for well over a century, but because no comet studied up close in this kind of spectroscopic detail had ever actually shown it happening in real astronomical conditions until 3IATLAS passed through. There's a bigger point buried in all of this that's easy to miss if you only focus on the individual numbers. Every one of these measurements, the carbon dioxide ratio, the isotope signatures, the nickel without iron, was gathered from a physical sample of material that originated somewhere else entirely, around a star or a stellar nursery, that isn't our sun and never will be, using no spacecraft, no sample return mission, nothing that had to physically travel there and back. Webb simply pointed its instruments at the coma as this object passed through our solar system on its way somewhere else entirely, never to return, and, in doing so, captured the most chemically detailed record of material from another stellar system that has ever been directly assembled by human instruments. Scientists have spent decades theorizing about how planetary systems form around other stars, what kind of ice and dust exists in those distant protoplanetary disks, and how radiation and time might reshape that material over cosmic timescales, largely working from models, laboratory simulations, and indirect inference drawn from studying our own solar system's comets, because actually reaching another star system to check any of it directly remains far beyond current technology, likely by many centuries at minimum, given the propulsion systems available today and any realistically foreseeable in the near future. 3IATLAS, entirely by chance, brought a physical sample of exactly that kind of material close enough for Webb to measure it directly, atom by atom, isotope by isotope, in a level of detail that would otherwise require a mission lasting many human lifetimes just to reach the nearest star system and back, assuming we even had the propulsion technology to attempt it at all, which we currently don't. That's what actually makes NASA's characterization of these findings as incredible holdup, without needing to reach for anything invented or exaggerated. Not a hidden signal, not a warning. A genuine, first-of-its-kind chemical portrait of material that forms somewhere entirely outside our solar system, shaped by processes, cosmic ray weathering sustained across billions of years, an exotic nickel release pathway never before confirmed in a comet, a layered internal structure releasing different volatile ices at different stages of its journey around the sun that scientists had, until this specific object arrived, only ever been able to theorize about from a distance, without any physical sample to actually test those theories against. And this entire body of evidence keeps building on itself. Each new observation, from the initial NIR spec detection in August 2025 to the ground-based VLT nickel finding weeks later, to the December MIRI follow-up, to the isotopic age analysis published in Nature this past June, has added another layer to a chemical case file on this comet that is now, by a wide margin, more detailed than what exists for the two interstellar objects that came before it combined, and arguably more detailed in some specific respects, than what exists for a fair number of comets that have belonged to our own solar system for the entire recorded history of astronomy. There's also a genuinely open question sitting at the center of all this that nobody has fully answered yet, and it's worth ending on, because it's the kind of question that keeps this story from feeling finished. If 3IATLAS really is carrying a cosmic ray cooked shell built up over 10 billion years or more, and if its nickel really is escaping through a chemical pathway nobody has directly observed in a comet before, then every future interstellar object astronomers eventually catch. And there will be more, especially as newer, more sensitive sky surveys come online in the years ahead, built specifically to spot these fast-moving visitors earlier and track them longer than Atlas managed to with this one. Becomes a chance to check whether what Webb found here is a universal feature of extremely old interstellar wanderers, or whether 3IATLAS just happened to be an unusually strange outlier, a single, unrepeated case that doesn't tell us much about interstellar comets in general. Right now, with a sample size of exactly one object showing this specific combination of chemistry, there's genuinely no way to know which of those two answers is correct, and that uncertainty isn't a weakness in the science. It's simply an honest reflection of how early we still are in being able to study these objects at all, given that only 3 have ever been confirmed. Every interstellar visitor discovered from here forward adds one more data point to a field that, as of 3IATLAS, has grown from 2 confirmed examples to 3, and every additional example meaningfully improves scientists' ability to say what's typical for objects like this and what's unique to this one specific comet. It's also worth remembering just how narrow the window was for any of this to happen at all. 3IATLAS spent an estimated 10 billion years or more drifting through the galaxy before its path happened to intersect with our solar system, on a trajectory that will only ever bring it through once, for a period of roughly 2 years from discovery to final fading, before it disappears back into interstellar space permanently, never to return, never to be studied by any future instrument, no matter how advanced. Every measurement described in this video, the carbon dioxide ratio, the isotope signatures, the iron-free nickel, the shifting post-perihelion chemistry, had to be captured within that narrow window, using instruments that happened to exist, funded, built, and fully operational, at precisely the right moment in human history for anyone to be watching when this particular object happened to pass close enough to notice at all. A few decades earlier, before Webb existed at all, none of this specific chemistry could have been measured with anything close to this level of detail. A few decades later, and this exact comet will already be billions upon billions of miles further out, far too faint and far too distant for any instrument currently being planned to ever study again. So here's what I'd actually ask you to think about. Webb didn't find a signal or a threat, or anything built by anyone. It found a chemical fingerprint unlike anything cataloged in over a century of comet science. Carbon dioxide, where there should have been water, nickel with no iron beside it, and an isotopic signature suggesting this object may be older than most of the stars currently visible in the night sky. Does a discovery like that, grounded entirely in real, published, peer-reviewed measurements, feel more or less remarkable to you than the alien spacecraft theories that dominated headlines about this same comet a year ago? It's worth remembering, too, that none of this was inevitable. Webb wasn't built specifically to study interstellar comets at all. It's fundamentally a general-purpose observatory, designed primarily to study distant galaxies, exoplanet atmospheres, and the early universe, and its ability to turn toward 3IATLAS on short notice, repeatedly, across nearly a year, required astronomers to successfully compete for limited observing time against every other proposed use of the telescope, and in some cases required special directors' discretionary time, specifically because the opportunity was too time-sensitive to wait for the normal scheduling process. Every single one of these findings exists because a team of scientists recognized quickly enough that this particular object was worth the effort, made the case successfully to a competitive review panel, and then did the painstaking work of actually extracting a coherent chemical story out of raw spectroscopic data gathered from tens of millions of miles away. That's not a small thing, and it's genuinely easy to lose sight of amid all the raw numbers and technical jargon. Let me know what you think in the comments below, and if you want to dig into the actual data yourself, NASA's own science site has the full June 2026 Nature paper, along with the earlier Webb and VLT findings, published and available to read in full, including the raw spectra that every conclusion in this video was drawn from, for anyone who'd rather check the primary source than take a video's word for it.